Good afternoon, everyone. I'm going to talk to you a little bit about the AMSAT Fox project, and I'd like to just start off first with how many of you are familiar with what AMSAT Fox 1 is. Okay, very good. Well, the Fox 1 satellite program, I'm going to give you a little review, the status of the program, and what we're looking for in the future. Why it is and what it is to start with. The Fox 1 development strategy is to take advantage of the growing CubeSat market, you would say. A lot of the rides to space have been scaled down. The CubeSat has become the model for what is launched these days. It's been developed so that it's easy to transport on the rocket. It allows a uniform size and dimension of the satellites so that they can pack many together and be able to launch them easily. So what we've gone for is to develop a family of CubeSats that have ham radio transponders that are also attractive to universities and other organizations that are flying their CubeSats to host their experiments, so they can fly their science experiments along with our transponders. The point being that this gives us a door to an opportunity for some launches that we used to find fairly easy access to launches over our history as ballast, but now that space has become so popular, we are actually competing with lots of organizations that have much money in order to make these launches, and we work with them to try to get launches through what's known as the ALANA, or Educational Launch of Nanosatellites program that NASA funds. And in that, actually, NASA is paying for our launch. We provide the satellite and they find the launch for us and pay for the launch costs. Fox 1 is AMSAT's first CubeSat. The smallest satellites we had prior to that were about 25 centimeters or 10 inches cube. And Fox 1 is 10 centimeters cube. That's about 4 inches. So it's really very tiny. It's a miniaturization that we haven't done before. Trying to get maximum power out of such a small device is really tricky, and it gives us a lot of challenges as far as trying to build a good, stable avionics bus that's going to not only survive in space without much shielding, but working with the off-the-shelf parts and such that we use is difficult, and the space to try to fit them all in on the small circuit boards. Have you been by the AMSAT booth? We do have a full-scale model of it there. This is the actual full-scale way to invite you to come by and see that. It's pretty impressive, because telling you the truth, working on this myself at my desk, and I've got a 21.5-inch monitor, so the thing is this big, at least, most of the time that I see it. And when you put your hands on it, it really gives you quite a difference. The whole point of AMSAT Fox 1 is to get us back in space, and then that gives us also a track record. We will have developed a CubeSat. It'll give us a place to go to continue developing more CubeSats in the CubeSat world. Fox 1 itself is a 1U CubeSat. We're going to carry a two-way FM communications transponder. It was designed primarily as a replacement for AO51 EasySat, which you can work with your HT and Aero antenna. We also are hosting experiments for a MEMS gyro that was developed by Penn State University students that's going to measure the spin and wobble of the satellite. The satellite being magnetically stabilized, it won't spin perfectly around the axis. There's going to be a little wobble or precession to it that we're looking for. Vanderbilt University is providing an experiment to look for low energy protons. And these are the types of events that affect us in what we do in the satellite industry, because radiation in space will cause upsets or latch-ups in much of the circuitry that is available these days. And they're going to study how much radiation they actually take in an orbit that is similar to ours. The Virginia Tech students are providing a camera with JPEG quality. It'll be a 640 by 480 picture that we will be downlinking pictures of the Earth, and it'll be high-speed data, so the pictures will be very clear, much better than the slow scan pictures we've had in the past. The mass 1.33 kilograms, and we'll have up to 800 milliwatts of RF power. This is a look at how the experiments are hosted. We actually have 4 slots that we have available for experiments on the top half of the bus, if you will, the top being the +Z axis. The red is in experiment slot 1 and 2 are the Vanderbilt. They have their controller in slot 1 and their sensors in slot 2, and then above that is the Virginia Tech camera. The experiment 4 slot doesn't have any electronics in it other than a thermistor for temperature sensing right now, but it does have a little cutaway to allow the Virginia Tech camera to peek out. And down on the IHU card is where we've located the Penn State University experiment, because there was room to put it there without having to have it on its own separate card up there on the bus. If you've attended symposiums or Dayton last year, you may be familiar with the Fox 1 bus diagram, or block diagram, sorry, because Tony's talked about this a lot in the past. So I thought this time what I would do is, for those of you who haven't seen it, introduce you to it, but also, as we've developed the satellite, introduce you to how it all fits together there. So we'd start with an uplink signal. The uplink's on 70 centimeters, and the antenna feeds directly off the Y panel to the RX card through a short piece of coax. The receiver card is going to pass the signal then to the IHU card. All of our audio is going to go to the IHU. The IHU is going to look for the 67 Hertz CTCSS, and it's going to process the audio, because we're going to add telemetry to that audio. We'll take satellite telemetry, and we're going to add it in the lower 300, well actually 200 Hertz of the audio spectrum. And we're also going to gather some of the science payload data. And we're going to put that together as what we call our slow speed telemetry, feeding that audio, which is your uplink signal, with the telemetry to the transmitter card. The transmitter card comes down on 2 meters. It'll be a very clear signal at 400 to 800 milliwatts. You'll have no trouble receiving that. And you're not only carrying on your transponder conversation, but we're also getting science along with it. If you go by the booth and you try the transponder that we have there, being a prototype, you will hear a little bit of a rumble in the voice there, in the ID or in your transmission. That's because we do not have the filter, the high-pass filter. We want you to hear that telemetry under the audio. Normally you would not hear that on your HT. We'll be filtering that so you don't catch it. But while you're talking on the satellite, you can also be capturing telemetry at the same time. This is a picture of the transmitter card, both the top and the bottom side of it. Recently completed. This will go in our engineering unit here, and you'd see the piece of coax coming out for the transmit antenna. The shielding that goes on the transmitter, and there's also one on the receiver. We had it engraved in memory of Tony, AA2TX. So those will actually fly on the Fox satellite, as well as the board that Barry pointed out at the top of the side. We've got 6 solar panels with 2 solar cells each. These are Spectrolab UTJ. They're about 28% efficient, and these solar cells will be on all axes of the satellite to provide about 2 watts of power. Each cell is about 1 watt of power, so a fully illuminated panel will give us about 2 watts of power. That runs to the power supply card. The power supply will regulate the voltage. It'll feed it directly to the bus. It'll also charge the batteries. This is a picture of the power supply system, another one of our engineering units. You can see that it fits fairly well on the card. The 4 connectors around the side here are where the solar panels will plug in to receive the power. The plus and minus Z come down through the bus connector, which runs right there. It's off to the left side as you look at it. The battery card has 6 A cells in pairs of 2, and this will give us around 3.6 to 4.2 volts of battery power, so that while we're operating in eclipse, everything carries on normally. And here's a picture of the battery card without the batteries yet. You can see that we have the room for the 6 batteries. They will be heated in order to keep them functional. These are NiCad batteries, and as long as we charge them at 0 degrees or above, that'll allow us to run tens of thousands of cycles if we keep the depth of discharge to about 20 to 25% max, and those batteries will last a long time in space for us. That's proven. The attitude control for the satellite, we use passive magnetic attitude control. It's basically just a rare earth magnet on the side of the satellite there you see, and this will keep us with the top or plus Z axis oriented toward the north magnetic pole. So the satellite will have some stabilization to it. As I said, it's going to spin and wobble a little bit. The interesting thing is that the satellite then basically points down as it goes over the North Pole and flips back the opposite way, coming around the south pole, the back end, if you will, is pointing toward the south magnetic pole, so it does a 360-degree flip in each orbit. The satellite's designed so that if the IHU fails during its lifetime, it will operate as a simple carrier-operated repeater. And this is to prevent any problems with, we lose our telemetry, we'll lose our science payloads information, but we still be able to operate as a carrier-operated repeater should that fail. So as long as the satellite's up there and illuminated by sunlight, if the batteries were to fail, then we'd be able to provide a working transponder. So for a look at the status, where we are, and what's coming up next, you probably read about it in the Apogee view or heard about it on the AMSAT news, but we have 2 launch opportunities coming up. The earliest of those is around May 1st, 2015. This is where ALANA 11 satellites were manifest. It's going to fly on the Air Force Ultrasat mission. Planned orbit's 389 by 700 kilometers at 58 degrees inclination with about a 6.5-year expected orbital lifetime. The mission that we were actually manifest on is the August 2015 ALANA 12. That's what we were chosen for, the NRO Grace mission. It's most likely we're going to fly on that. But NRO has asked all of the CubeSats that are flying on both missions to be delivered in October so that they have the opportunity to fly whatever they need to or whatever they can on the earlier mission. We don't have control over which one we're going to get because, we're hitching a ride. It's like hitchhiking along the road. Whoever picks you up, you go where they're going and you play by their rules. Our actual orbit that we were manifest for is a higher orbit at 470 by 780 kilometers, which will give us a little bit more coverage. It's a little higher inclination, take it a little bit farther north and south. But the biggest difference there is that the lifetime expected is 11 years. And we do, while the satellite was designed for a 5-year mission, we do expect that it should be able to last the 11 years in the higher orbit. So I would say that while it would be fun to get a sooner launch, it's probably more likely that we're going to have the fall launch. This is an example of how we get there. It's going to be on an Atlas V rocket. And if you see the aft bulkhead carrier is at the bottom of the Centaur upper stage. This is where the CubeSats are attached for flight. They fit into, and this is an example, so the outset is irrelevant to the discussion actually, but that's the box that the P-pods are put in there. There's up to 3 1-unit satellites or 1 2-unit and a 1-unit or a 3-unit that go into a P-pod, which is the polypico orbital deployer. It's just a box with a lid and a spring on it. When the lid is open, the spring pushes the CubeSats out and you're on orbit. They mount several of those at the bottom of the stage. Fly us up to orbit. They get rid of their primary payload first, and then as the stage descends a little bit, they do a burn to take us safely away from it, and then they'll spit out the CubeSat, so to speak. And you've probably seen some video of that, of either being launched from ISS or some simulations of them being launched from actual vehicles. So for this year, for Fox 1, for our status, the milestones we're looking at is that here in May, we've begun work on the engineering unit integration and testing. This is where we take all of the systems, put them all together and run it as a satellite. Test out everything to make sure that they're all happy with each other and that everything functions the way we want it to. We'll actually be taking the stack of boards to start with, and once we're satisfied that they're all working, because it ain't going to work the first time, and we're done taking that apart and putting it back together a couple times, we'll proceed to putting it in the actual space frame and working with some of the other things such as the antenna deployment and stuff. So it's going to span, hopefully in 3 to 4 weeks we'll be able to get through that without, and when we have no major problems remaining, then we move on to our critical design review in June. This is where we actually take our last look at all the test results, everything that we've done, the systems that we have, and we say, is this going to fly? Can it fly? Do we have any concerns about what's going to happen with this thing? Because the thing about the satellite is once we turn it over to the launch provider, we can't do a thing about it. If it doesn't work then, it's too bad. And we can't afford, of course, not to give them something that breaks later. So we get a bunch of experts together to look that over. Once we've completed that, we'll actually build the flight unit and the flight spare. Both of them will have all of the flight boards. They'll have all of the solar panels and solar cells on them, and we've put it through what we call a day-in-the-life testing, where we actually, it's basically the same as it was with the engineering unit, but we're running it for 4 to 6 weeks anyway, and using it as a satellite in somebody's garage. Well, actually, we've graduated from garages to houses because this thing's so small, you know, you can take it into your office, actually. So we're moving up. We can have air conditioning now. And it'll also fit in your freezer if we want to test it for cold climates and such like that. But we'll run it through that. We test the heck out of it. We throw everything at it that we can to make sure that there's nothing else that comes out of that. If anything comes up, we're going to tweak it and fix it. And then in August, we'll be done with that, and we'll move on to taking it to the vibration testing, where we subject it to on the order of 25 Gs in some cases on some of the axes. This is to make sure that when we're launched, things don't shake loose and things aren't falling out, and the components that we have in there don't come unsoldered or anything that would be untimely that would cause that failure that we can't do anything about. We put it through vibration testing, then we put it through what's known as a bake out or thermal vacuum, where it is heated for 6 hours to 60 degrees C in order to remove any residue that might be from even our fingerprints, although we use gloves, or any of the glues that we used, or any other type of polymers and what have you in the satellite, that in space, if you have this stuff in there, and once you get up in the vacuum, and it's going to start to leak out, and it's going to be flow, you know, there's no atmosphere, there's no gravity, so all these little molecules of gook would start leaking out, and they would go, oh, here's a nice cool camera lens, and they park right on top of that, and you lose your picture. So the point is to bake everything out of it that we've got. September we'll have our mission readiness review. October the thing has to be completely done, and NRO says you can put it on the shelf, you can charge the batteries, but you cannot make any other changes to it. So it's hands off. It sits on the shelf until January of next year when we deliver it. So that's the way it goes when you're hitching a ride. The flight spare, assuming we don't need it when we go to launch, will be used. It will take out the experiments that were in it, and we'll put the RAD-FX sat, which is another Vanderbilt experiment, a little bit more detailed than the one they're flying on the Fox 1A. We'll add their experiment, which has also been selected for a Alana launch, although we don't have an exact date on it yet. It hasn't been manifest. We'll put it through the tests again, and we'll be ready to hand that over. Vanderbilt says they're looking at the second half of next year that they'll be ready with their experiment. So sometime, hopefully, maybe the second half of 2015, probably more likely earlier 2016, we may get a launch with that. It will have a different set of frequencies, but the same FM transponder, same slow speed telemetry, same high speed telemetry. It's a copy of Fox 1A with different experiments flying on it. So for Fox 1C and D, as we call them, we're actually building 4 units so that we can have 2 on the shelf ready to fly. And this is where y'all can help, besides joining AMSAT. But we're looking for partners, universities that have experiments they want to fly. You have experiments that you want to take care of. You can put all your time and money into making a great experiment, and we'll get your data to the ground for you. And of course, we've got a network of hams all around the world, excuse me, that'll be able to capture this telemetry for you. It can run in high-speed mode if you need that. It can run in low-speed mode. If we run it in high-speed mode, when you're done with your science experiment, we would ask that you turn it over to us to use the transponder portion from the amateur radio. But we have 4 slots, and we have an ICD for what's available there. Anybody has any offers or desire to fly something, please get a hold of us, because we'll have 2 more ready to go whenever that's available. And beyond that, we have Fox 2 that you've probably heard of before, and even beyond. But Fox 2 is going to build on the heritage of Fox 1. What we're learning by trying to cram things into a 4-inch cube is an amazing amount. There's a lot of work that goes into taking commercial off-the-shelf parts, which are in our amateur price range of doing things, and putting them into a tiny satellite. For one idea is the challenge that we have with the density of parts on the board. I mean, you can only fit so much. You don't get the whole 4-inch board for that matter. And we're using 4-layer boards, and the density of the parts can get pretty crazy. A 3-unit CubeSat, of course, gives us 3 times as much room, 3 times as much power, and that is a good part, because then if we get into running like a transponder, which takes more power than a simple single channel, we can run with more power, more modes and bands, and possibly some attitude determination and control, so that we can point higher band satellites down toward the Earth development is underway for this. We're always looking at what's going to happen next and talking about what's going to happen next. Although our primary focus is Fox Run right now, of course, because that gives us what we need to learn for Fox 2. And beyond that, there are lots of CubeSat opportunities. It was mentioned by the launch providers that they don't see that the CubeSat market has reached a plateau yet. There are still, it's a growing segment of the space industry. So that means growing opportunities for us to be able to partner and get more launches. The sizes are getting bigger. Actually, our 1 unit is much less common now than 3 units. 3 units are kind of the more common, but they've even gone to 6 and 12 units. And so that's another opportunity to get more power, more space, more agility out of a satellite. The possibilities are expanded as well because you can get into flying formation of satellites and propulsion even. Now, Alana launches don't allow propulsion, so we're not going to get one with our free launches with them. But depending on who we partner with, we may find some people that have a propulsion system that they're testing, want to fly our transponders with them, and we can get pushed up to a higher orbit. I did not say HEO, but I said higher. And we'll work our way up. You know, everything develops so quickly. I mean, it's amazing what CubeSats can do and are headed toward doing. So even though they're tiny, they're quite capable. We're looking at several possibilities and partnerships. We're always looking for ways to get to space. It's not like we go, oh, we've got Fox 1 and that's all we're going to do. We're always out looking for new opportunities. There are a number of AMSAT members who I mean, we're such a diverse combination of members that there are people that it's easy to reach out, or friends, partnerships, people at various places they work, that you run into these opportunities, and that helps us out a lot. And if you'd like to help, if you really want to help in the construction and building of the satellite, we need people who have engineering, mechanical, electrical, PCB, all of the things that you see listed here, from construction, from RF circuitry to DSP, even systems engineering, project management. There's a lot of things that go into building a satellite. You know, it's not quite as easy as just taking a radio and sticking it in a cube and getting it launched or something like that. It has to be engineered to last a long time in a very harsh environment. And so it takes a lot of work and it takes a lot of dedication, but there are a lot of people out here. Hams, we're like that. We know a lot of neat stuff. We may not know everything, but you might know something really special. And if you want to share that and help be part of this, please get a hold of me, because it's all volunteer. You know, everybody does a little bit here and there, and we get something done together. So I appreciate that. And that's all I have with that. Is there time for a question? 1 or 2 questions. Sir in the white shirt. Okay, what do the antennas look like and how are they deployed? Each of them is a vertical antenna, a whip. There's one on each y-axis. The 70-centimeter antenna points up, if you will, so it's just a quarter wave piece of wire. If you come by the booth, you can see a representation of that. The 2-meter is on the opposite face and pointing down, if you will. And what they do is we coil them around some stays, some stands that are on the face of the Y panel, held down by a fishing line, which is tied around a resistor. The resistor is a high temperature resistor. When it comes time to fire them, we light it up, it melts the fishing line, and they're going to be nitinol or nitinol spring, so it'll spring into the antenna shape. Okay. Any others?
It's in the launching, physical launching. The box springs, the lid pops out.
Uh-huh.
It's not very precise for setting something in orbit.
The question was about the P-pod, the deployment from the P-pod. Sticking it in a box, opening the lid, and shoving it out with a spring doesn't sound very precise for orbit. And you're right, you get what you pay for. We're going to be in orbit. It's going to be at a certain height, and once we're there, given that it's a high enough orbit, you know, if you launch from the ISS, you're up there a few months. In the 470 by 780, we'll be able to stay up there for up to 11 years. Part of the secret is to put as much mass into it as we can. We're going to add a little ballast, actually, in order to make it all of the 1.33 kilograms that we're allowed, because that helps it stay up. As far as attitude determination, they come out and they're tumbling or facing, however. That's what the magnet is, to eventually bring it into some sort of alignment so that the antennas are basically parallel to the Earth. Of course, as you get a little farther north, you know, it's going to tip down slightly, but rather than being completely vertical to the Earth, we've at least got them more or less horizontal to where you are. All right? Thank you very much. If you got any more questions or anything, please come by and see us. Come by and see us if you don't have questions, and we'll show you what we've got. Thank you.